Tonight, we're fortunate to have Kevin Wilson, who's going to talk to us about stellar spectroscopy for amateur astronomers. Kevin has just recently come to this region. He's originally from, most recently from Maryland, and he's started doing astronomy at age 12 with his first telescope, and has continued on since then. He's been vice president and director of the observatory of the Astronomical Society of Greenbelt in Maryland, and he's a graduate of Carson Newman, double majored in religion and political science, went on to get a master's divinity and sacred theology from Yale Divinity School, and then a PhD in Hebrew Bible, Old Testament, and Northwest Semitic philology from Johns Hopkins University. And he's taught, he's been in some interesting places, namely Lithuania, and North Andover, Massachusetts, Sewanee, Tennessee, and Waverly, Iowa. So with that, I'll turn it over to Kevin, and he can do his presentation.
Thank you, Don. For those of you who don't know, it said I was at the Astronomical Society of Greenbelt, which, by the way, if you name your club an astronomical society, people expect a lot more of you. If you don't know, Greenbelt happens to be where Goddard Space Flight Center is as well, and our club started out as part of Goddard, the Goddard Astronomy Club, but in '92 they decided you had to be an employee of NASA to come on campus, so we had to start our own club. But we still got a lot of great speakers. In a way, it's like here, you all have access to ORNL, and we had access to all kinds of people from Goddard and the Smithsonian, and even from as far away as Green Bank, West Virginia, where the National Radio Astronomy Observatory is. The topic for tonight, well, that's not right. I'm speaking about spectroscopy tonight, not colonoscopy, a topic about which I don't know enough to speak for an hour, at least not in an entertaining fashion. The one thing I do know about it is you don't want it done with the Schmidt-Cassegrain telescope, because that's going to be unpleasant. But this is something I became interested in. The smaller the aperture, yeah. But definitely use the full color camera on that. This is the Hercules globular cluster, which I'm sure most of you are familiar with, M13, easily visible through binoculars. It is 11.65 billion years old. It is about 22,000 light years away. It has a rather low metallicity compared to the sun, meaning the metallicity is generally calculated as the number of iron atoms divided by the number of hydrogen atoms. And if it's in negative, that means it's lower metallicity than the sun. And if it's positive, it's higher. And the brightest star there is a red giant with a surface temperature of 3,000 Kelvin. Now, we've all seen this. This is not something new. But none of us has ever been there. None of us was around 11 billion years ago to observe it being formed. None of us have gone there to test the metallicity. We haven't stuck a thermometer in one of the stars to find out. So how do we know all of this about something that is that far away? Indeed, how do we know how far away it is? Colonoscopy? Colonoscopy, yes. Yeah, you can see the polyps there on the right. So I'm going to be talking about three things tonight. First off, what is spectroscopy? Second, what can we learn from spectroscopy? And third, how can we as amateurs do spectroscopy? In spectroscopy, our interest is in the visible light range. There's also spectrographic information to be gained in the ultraviolet and the infrared parts of the spectrum. But of course, UV and IR don't penetrate the atmosphere very well. And we don't have cameras that can detect them anyway. That's why all of those have to be space-based observatories. But we're interested in the wavelengths between 3,800 and 7,500 angstroms. And stellar spectra are the spectra of light that we receive from stars, and then they're broken out into their various components, as you see here. And there are two types of spectra, just as there are if you've done Earth-based spectroscopy with any kind of materials. You get absorption spectra and emission spectra. And we're usually looking at absorption spectra when we're looking at stars. If you're looking at an emission nebula, then you'll be looking at emission spectra. But in the absorption spectra, what happens is when the light runs into other atoms, those atoms will absorb light at certain frequencies, and I'll tell you what determines what frequencies here in a minute. And so when the light gets to us, it's had those frequencies yanked out. And with an emission spectrum is at some point that atom that got bumped into is going to try to give up that extra energy that it absorbed, and it will do so at the same frequency that it absorbed it. And so you'll notice if you squeeze the two together, you'll have a complete spectra once again. And the most important spectra series that we look at are the hydrogen. And there are three different spectrums. There's the Lyman series, which is only visible in the UV range. There's the Paskin series, which is in the IR range. And then of most important interest to us is the Balmer series, which is in the visible range. And just a bit of Maryland trivia. Balmer is how you pronounce Baltimore if you live there. In the Balmer series, what we have are the absorption of light by hydrogen atoms that are already excited. They've already been hit by previous photons, and therefore they have their electrons in the second level, the second shell. And the Balmer series is created when a photon strikes one of these, and you get the jump from second to third level, second to fourth, second to fifth, and second to sixth. And those are different frequencies of light that are absorbed. That's the amount of energy it takes to bump one of those up to a higher level. And then you'll notice when we look at the spectrum, there we can see the 4 different lines that are missing that have been taken away by that hydrogen and absorbed into the electrons. And although hydrogen is the most important for us as astronomers, of course, every element has its own particular fingerprint. No two elements absorb in the same range. And so if you have a particular set of absorption lines, you can match those up, and it will always indicate one particular element. Aha, we know hydrogen, that this light encountered hydrogen at one point in its journey, or sodium or nitrogen. Now, the issue is that if it's hit both hydrogen and oxygen, you'll see both sets of absorption lines in there, and so you have to separate those. You have to identify what belongs to which elements, and that will tell you, oh, this is run into both hydrogen and oxygen along the way.
Doesn't that get really confusing though, if you have like, let's say one element is emitting and another element is absorbing in between? Doesn't that get terribly complicated to tell which, from the final result?
Well, it would have to be a direct line between us and the star, and it would have to be significant enough to actually fill up the emission spectra in there. It can happen, but generally it's not going to.
So you're saying you'd still be able to see contrast?
Yes, because what's happening is the light, we're only seeing the light that comes straight from that star. So everything is coming straight toward us. Any intervening atoms, when they release their light, they can release them in any direction. And so the chances of it being in our direction and perfectly aligning with the light that's coming from the star is going to be fairly low in those instances. So how do we build a stellar spectrum? Most of the collisions between gas and light do not occur out in empty space. It does when you have a nebula and you're trying to do a spectra of that nebula, but most it's coming from the star itself. And so of course light is created in the core where nuclear fusion is happening. It then has to propagate through the convective zone where it runs into a bunch of atoms. And my understanding, I've never seen the calculations behind this, but I've been told it takes about 1 million years for light to get from the core of a star to the outside of it. So it's bouncing around in there for a while. And then it gets to the photosphere where it is emitted without all of the frequencies that it's lost along the way while it's bouncing around in there. So what information can we learn from spectroscopy after we've gotten these nice spectra in hand? One of the first things is we can learn stellar composition. It tells us what a star is made of. Now, most stars, when they begin their life, are mostly hydrogen. I mean, almost everything in the universe is mostly hydrogen. The universe itself is mostly hydrogen. But we can identify any other elements that are present. This is the spectra of the star Vega, which is a very bright white star. And you can see the 4 distinctive hydrogen absorption lines there in the spectra. This is the spectra all the way from the blue to the red. And these are known as hydrogen alpha, hydrogen beta, hydrogen gamma, and hydrogen delta. And then you get a bunch more that are also from hydrogen. They start bunching up and coming so quickly, it's just a royal mess over there. And for most of us, this is right at the edge of what our camera can detect anyway, so we generally just ignore them. So it lets us know what elements are in the star. As a star progresses through its lifetime, it first is turning hydrogen into helium, and then helium into oxygen and carbon. So we can tell whether and how much oxygen there is in the star, how much carbon there is in the star. And we can also calculate stellar temperatures. What we do is we look at the wavelength of maximum intensity. In other words, when we look at this spectrum, where is the peak? Where is the high point of it? And these are spectra for 4 different classes of stars, O, A, G, and M, down through there. And so you can see that the O-class stars continue going up off to the right, off to the left. And actually, for the top 3 classes of stars, the hardest ones, their maximum intensity in the spectrum is in the UV range. So we can't detect their maximum intensity as amateur astronomers. But any of the other ones, for the second one, the light blue, you notice it's somewhere a little over 4,000. For the green, which is a G-class star, we're somewhere around the 4,600 angstrom. And for the red star, which is the orange line, we're looking at somewhere around 6,000 angstrom. And if you take that maximum intensity, you can use Wien's law, which is misspelled here, it's W-I-E-N, Wien's law, which is a constant divided by the temperature will give you the wavelength at its max. And since what we know is the wavelength at the maximum intensity, and we know the constant, that will allow us to solve for T and get the temperature. And the temperature that we're calculating is not the temperature in the core, it's the temperature of the photosphere itself, where it's leaving the star. We can also calculate stellar distances. That's how we know how far away the Hercules cluster is. Because if you determine the apparent magnitude, which you just do by observing, you can then find the absolute magnitude based on the surface temperature that you discovered in the previous step. So if we know that a star has an apparent magnitude of, say, 9, but we know that its real magnitude at the source is a 6, then we can calculate the distance because light falls off at an inverse square ratio. So we know that if it looks like a 6 to us, or a 9 to us, but it's really a 6, we know that's how much it's fallen off between us and theirs. So that will give us the distance.
That inverse proportion talks about the density of photons, not their color temperature.
No, it's not based on the temperature. We use the temperature to find the absolute magnitude. But then that will give us the absolute magnitude at the source because it gives us a flux.
What does the absolute magnitude mean relative to this?
Absolute magnitude is how bright it is if you were standing right there, right? And that drops off over distance. Things that are farther away appear dimmer, right? And that falls off at a regular rate that we can calculate. And so if you know how bright a light is and how bright it appears to be, you can then calculate the distance from you to that object. We can also talk about stellar evolution, the lifetime of stars. And by the way, for those of you who are members of the Astronomical League and are familiar with their observation programs that you can complete and get nice little pins for, they have a very nice one for stellar evolution. That is one that you earn on the way to getting the spectroscopy certificate. So I grew up in Scouts. I'm used to getting badges for everything. I don't like that as an adult, nobody gives you badges for completing things. They just give you another task. So I like getting badges. I like that y'all hand out the stars for the occultations on there. So, but stellar evolution can be determined by creating what is known as a Hertzsprung-Russell diagram, which is what you see here. And the Hertzsprung-Russell diagram is a plot of the temperature of the star, which is on the horizontal axis, against its luminosity compared to the sun. Luminosity here being apparent magnitude, absolute magnitude there. And so the stars that are in the upper left are much brighter than the sun. And notice this is on a logarithmic scale, so they're a lot brighter than the sun, but they're a lot cooler than the sun. You can see our star right there, marked sun, nice and handy, is a yellow star that's at around, I think the actual Kelvin is 5,300 Kelvin for our star. But those that are much brighter are higher than us. Those that are dimmer are lower than us. And all stars begin their life in this line that you see running down diagonally from the upper left to the bottom right, what is called the main sequence. All stars will begin their life there. So our star, as you can see, is a main sequence star and has been for about 5 billion years, and good Lord willing, will be for another 5 billion years, give or take a Tuesday. The high and medium class stars, meaning anything kind of yellowish orange and upward, will then, when they've burned up all their hydrogen, they'll start burning helium, and they will expand because helium produces more heat. They will expand, and the medium mass stars will become giants. The high mass stars will become supergiants. Once they've finished burning all the hydrogen, they'll start burning whatever they have left. Our star will never burn anything heavier than helium, so it'll be done at that point. And at that, they all begin to shrink and cool, and they all move down into the white dwarf areas. Now, the supergiants will burn longer with heavier elements and then explode violently. And then they will collapse either to a black hole or a neutron star, depending on their mass. If they're heavy enough, it's a black hole. If they're not heavy enough, they're a neutron star. Yes?
You said that you get the surface temperature from the spectroscopy.
Yep.
And from that you can get the absolute magnitude gathered by looking at this plot. But there is some spread, and it's not a perfect line, so there is some spread in the luminosity you would get.
You would, but keep in mind this is logographic, so that line would appear a lot straighter. If this were on a regular scale, it'd be more stretched out and we'd be more or less straight. Some things are locally curved, unlike the Earth, which is locally flat. Right? Now, the low mass stars, the very red ones down at the bottom, they will never leave the main sequence. They will eventually burn up all their hydrogen. They will not have enough mass to ignite the helium fusion, and they will simply slowly cool over billions of years, becoming brown dwarfs, and then completely left. Because by the time a star is a white dwarf, it's not producing any energy. All the light and the heat that we see coming from it are left over from what it created during its lifetime of fusion. It's just a big, dead, very hot, very bright rock that is slowly giving off its heat as radiation and cooling to the, until it gets to the bottom. And this will happen for the red stars, except they'll never get to blow up to be anything. Stars at the top left that are the most massive burn the hottest and also burn the fastest. They will have much shorter lifespans than, say, our sun will. And the things below us on the main sequence are going to have much longer lifespans on the estimated range of trillions of years. In other words, there's no star that's down in that bottom right-hand corner that has yet to burn out. The galaxy, the universe hasn't been around long enough for that to happen. And from that, we can divide the stars into stellar classes. And this is a classification known as the Morgan-Keenan system. They used to be in alphabetical order based on how intense the hydrogen lines were. And then they realized, wait a minute, that's not what we should be classifying on, because a lot of those that were in different categories should have been in the same category. So we now have this unalphabetized mess to deal with. And the O class are the ones that are at the far upper left. The M class are the ones that are the cool red ones at the bottom right. And each class has a subclass, 0 through 9. So it will go O0, O1, O2, all the way up to O9, and then to BO, which are the smelliest of the stars. Right? And then they also have a Roman numeral that tells you where it is on the Hertzsprung-Russell diagram, where it is in its lifetime. So Roman numeral 1 for the supergiants, 2 for bright giants, 3 for giants, 4 for subgiants, and 5 for main sequence stars. So in this classification, our sun is a G2V. And as with most things in astronomy, they've come up with a nice mnemonic to help you memorize the stellar classes. O, be a fine guy, girl, whatever you're into, kiss me, right? My favorite mnemonic was one that I heard for remembering the planets in order, which was Mary's virgin explanation made Joseph suspect upstairs neighbor. These are the things you learn in seminary. By the way, I learned something fun today. I love collecting fun facts. I found out that orcas sometimes hunt moose. Apparently moose are really good swimmers, and off the coast of Alaska, they'll go swimming, to cross to another peninsula or to an island, and the orcas will chase them down and eat them. Oh, Canada, why did we let you be a country? Now, with the stellar classes, we can create an idealized spectrum. This is what the spectrum should look like if it was full for a star, using Planck's law. And they're just to remind you of Planck's law in case you've forgotten it. The B nu T is if you know the wavelength, the frequency and the temperature, then you can calculate this out as changing the frequency as you go across. And this gives us the idealized spectra for each of the classes, and you can see them labeled up at the top right. And as I said before, many of their top points, their areas of highest intensity, are in the UV range. The gray indicates the UV and the IR, and the white is what's in our visible range. So I know you're asking yourself by this point, how can I, as an amateur, do spectroscopy? Or you're asking, when will this guy be done? Here are the things you need in order to be able to do spectroscopy. A telescope, which I'm assuming most of us have in some form or another, and it doesn't really matter which one you have, almost any of them will work. You need a camera. Usually this is an astronomy camera. And oddly enough, even though what we're mainly concerned with is the spectrum, black and white cameras work better for spectroscopy. They're more sensitive to light. You don't have to demosaic them. If you're unfamiliar with that term, if you haven't done astrophotography, there's a set of sensors that receive the light, and they're in a square formation of generally blue, green, green, red. And they combine all four of those in a process called demosaicing in order to get the single color that represents. It's also simpler to process black and white images. There's no color correction to be done at all. Color cameras work almost as well, but not quite. And given how cheap the black and white cameras are, it's generally worth it to get one. You can also do spectroscopy with a DSLR. There is a device that you can attach. It clips on like a lens cover that you can just reach up and click. I mean, you'd want it on a tripod or something. But it can be done with the DSLR camera. You need software to be able to analyze the spectra. And there's many of those out there, and most of them are free. VSpec, RSpec, ISIS, not the terrorist group. And I don't know if it's BASS or BASE. I think it's BASS, but I don't know. But these are all free to use to analyze the software, analyze the spectrum. And then you need a spectroscope. And this has been the sticking point for the majority of amateurs because spectroscopes are expensive, like really expensive. I mean, even compared to other astronomy equipment, expensive. Commercial spectroscopes, you've got the traditional ones that have the prisms, multiple lenses, and use a slit so that you're only looking at what you want to look at. And these will generally run you in the $4,000 to $5,000 range. And this is what the pros use. A little cheaper is what's known as the Alpi 600 that you can get for around $900. But fortunately, there recently came on the market what's known as the Star Analyzer 100. You can also get a Star Analyzer 200 if you've really got the money, which is about $50 more, I think. And it's called the Star Analyzer 100. What it is a diffraction grating embedded in a filter, and this is a standard size 1.25 inch filter that screws on just like any of the ones we have. But it has a diffraction grating built into the glass, and it's called the Star Analyzer 100 because it has 100 diffraction lines per millimeter. It's fairly dense. And that, yes?
Wouldn't a simple slit and diffraction grating work like they used to use?
You're not going to get the precision. I mean, we can make a slit, but the ones on the top there, the traditional ones, have a lot of other lenses in there that will correct for different aberrations as the light comes through and give you a better image. And so now we have the SA100, which is reasonable by astronomy standards. I mean, nothing we buy in astronomy is reasonable by normal standards. But you can get a Star Analyzer 100 for about $175. And then you go out and you acquire images. Because this is not a slit spectrometer, normally you have a slit so that only the light comes in from the single thing that you're trying to image. And if you want to do a nebula, an emission nebula, you're going to need a slit. But here you can see what you get just shooting a general area of the star. You get the star itself, and that's the 0 point image. That's what's coming through without being refracted. And then you get the diffraction grating sending the light off in both directions. So you'll notice every dot has spectra, sometimes multiple ones, on both sides of it. And the one that you want to use is the one on the right. You notice those are all a little brighter. This is what's called a blazed spectrometer. It makes that one brighter than the others. It sends more light in that direction. And you can see one of the problems that you have, like this one right over here, the second dot from the right, you've got two spectra colliding there. And this is one of the problems that you get with without a slit. And so you have to be careful to make sure, and generally what you want to do is have it zoomed in enough, and you do that by changing the distance from the filter to the sensor on the camera. You want it to fill up your entire screen. You want to have the image of the star and then the blaze spectra, and that's it going out through there, because that gets you the highest resolution on the spectrum. And if you're doing color, you'll want to do all the calibration that you would with regular color using flats, darks, and bias images. And once you've done that, you want to crop them so that you have the image of the star on one side and the spectrum on the other side, and have them horizontally flat there. Don't do any nonlinear enhancements, because that's going to give you a different spectrum than what you had before. No stretching or anything like that. And you can see in both the color and the monochrome, we have little dark lines. That's the Balmer series that we can see there. There's the 3 on the left, and then 1 over into the red. It's a little harder to see on the color one, but you can actually see with your eyes the spectra and the emission lines that we're looking at. And then you load that image into your spectroscopy analysis software. This is RSpec. And one thing I found out, this is generally true of the astronomy community in general, but I had a question about spectroscopy, posted it on a board dedicated to spectroscopy. And within an hour, I had an answer from the guy who had written the book I was using and the guy who had written this software. Both of them had responded, letting me know how to fix my problem there, so it's very helpful. So when you first load your image, what it's measuring is each vertical column across there and giving you the intensity of light within that. So you see we've got very intense light here. This first column represents the image of the star itself, and then we get the spectrum over here on the side. And at each point, it represents how bright the light is at that point, with dips indicating places that there are absorption spectra. And what you'll do at that point is then calibrate your spectrum. You pull up this little dialog, and in the top box, you click at the highest point on the star image, and that tells you that's the 0 wavelength. And then you click on the hydrogen beta line, which is the second one. It's the one almost toward the top there, which is 4861 angstroms. You click on the bottom point of that, and that tells the image where those 2 spots are and allows it to calculate how many angstroms per pixel in your image. And you can see up at the top, it actually says angstroms per pixel. In this case is 11.2. And once you've done that, you can then zoom in on the area that is the spectrum, and you begin analyzing it. And this program has a nice pop-up that will highlight particular absorption spectra. Here I've clicked, I said, show me where the hydrogen Balmer lines should be. And you notice that those line up with the dips on the spectrum quite well. Again, with the messed up section at the right, to the left of the camera, being ignored. And this program will also allow you, this is a spectra of Vega that I took. And I happen to know that Vega is an AOV, which means it's an A class, very beginning of the A class. V means it's a main sequence star. And this line that you see here is the actual spectrum of Vega. And you can see that the dips are lining up fairly well with the one that I took. But then there's a problem. Other than the dips lining up, you may notice that my spectrum looks like a big hill. Theirs looks like a gradual incline. And that's because we need to calibrate the spectrum itself to take account of the quantum efficiency of the camera. Yes?
What's the noise?
Which noise?
Well, if that was straight spectra, those lines would be straight. You've got something super high frequency imposed on all those lines. What is that?
I don't know. That's a professional. This comes with the professional library of spectra. I assume that may be just other atoms it's encountered along its way, because it's going to bump into other stuff. I mean, and that is just a guess. And keep in mind, I have a PhD in Old Testament, so what do I know? Right? But the problem with the camera, as anyone who's worked with one for astrophotography knows, is that cameras don't receive light equally at all points on the spectrum, which is a problem that it shares with our eyes. Our eyes don't see red and blue anywhere as well as we see green. And the cameras are the same. Notice they've got a lot there in the green, and it's dropping off toward each end because it doesn't read. I mean, if you know this already, if you've ever looked through at the Orion Nebula just through an eyepiece. We're like, where's my purples and reds and pinks? Why is it green? And the reason for that is our eyes pick up the green easier than they do other colors. And the camera does too. So there's a math function in here that lets me take the professional spectrum and subtract my spectrum from it. And that then gives me a correction curve. And I can do math using that correction curve on any future spectra I take. And that will adjust my spectra so it takes into account the color sensitivity of the camera. And so here you can see it's looking a lot more like what it should look like. The dips are nowhere as intense, simply because the camera that I was using is the 14-inch Schmidt-Cassegrain that will not hold a calibration to save its life. It's the one that the Astronomical Society of Greenbelt has. And when it was 40 years old, it was given to us by the local community college, because that and the observatory were sitting on top of their building right in the spot that they needed to put an HVAC machine. So we benefited from that, but it was already, 20 years ago, a 60-year-old scope. And so if the more you're able to focus, and also the better you're seeing, because the better you're seeing, the smaller the image of the actual star will be in the sky. And so the spectrum is not going to, if you've got a wide one, you've got light being diffracted from both sides of the star, and that bleeds into the areas that are the emission, the absorption spectra. So, and there are some people that will actually, because what you want to focus on when you're taking the spectrum is the focus of the spectrum. But keep in mind, that's light that's traveling multiple paths to get to the sensor. So if you're focused on the blue side, it may not be focused on the red side, because those are different lengths from the grating to the sensor. But there you can see a general idea of what you're going to be looking at. Recognized.
Does the bit depth of your camera have something to do with a 16-bit camera versus 1-bit?
Not really, because, obviously, you'll get more accurate readings on the intensity there. And having a good deep well on the pixels is important, especially for shooting stars like Vega and Rigel and other really bright stars. Because with really bright stars, you're shooting like half a second of exposure time. Otherwise, you're going to get really washed out. And then the spectrum starts bleeding all over itself, and you get useless images. When you're doing something like a magnitude 6 star, that's when you're going to you don't need the well depth as much. And that's when the stacking becomes much more important. So,
No.
it's done.
The official spectrum probably was also done with a grading.
Yes. Yeah. This is the official specter is from the Pickle Library, named after the guy who pulled it together. And that, I believe, is it. Any other questions? Yes.
In the beginning, you mentioned the hydrogen to iron ratio.
Yes.
Would you expand on that as age or iterations of the star collapsing and being reborn?
In astronomy, anything heavier than helium is considered a metal. And so the more metal a star has, a star will generally have more metal the older it is, because it's creating these heavier elements as it goes. Especially, we get things up to, what's the heaviest thing that can be made in a star? Is it iron? Iron, yeah. I think it's iron. I mean, for any heavier elements, you're looking at black hole collisions or supernovae, like that. But then also you have different generations of stars. You've got population 1 stars, which are the most recent stars. Our star is a population 1 star. Population 2 stars are the generation before. Most of those stars in the Hercules cluster are population 2 stars. Population 3 stars are theoretically the earliest stars in the universe, and last time I checked, we didn't have any pictures of any of those. Maybe Webb's come up with some since then. But keep in mind that the first generation of stars would have very low metallicity because they were all hydrogen, because everything was hydrogen, right? But those along the way created heavier elements and then exploded, sending those out. And then those elements gathered together in dust clouds and condensed to form the population 2 stars, the second generation of stars. And so those would begin with more metallicity than the first stars did. And then when those explode, you're going to have even more metallicity. That's why our sun has more metallicity than earlier stars, which is one of the reasons that the Earth has enough metallicity for life to start here. Because all that was present in the dust that made up the solar system and collapsed to form the star. And so the metallicity index indicates the age of a star, but also, if we can also determine the age from another step, which we can do because we can calculate how long a star stays on the main sequence. If we know its mass, then we can say, our sun, it will take 10 billion years to burn up all of its hydrogen. And so in a large cluster like the Hercules cluster, what you do is find what proportion of the stars have moved off the main sequence. And that will give you an idea of how old it is. Because if it's older, more of them will have had time to mature and move off the main sequence. And when we look at those population 2 stars, we see more metallicity that is a result of earlier generations of stars. And when we look at more recent stars like ours, then we're looking at stars that have an even higher metallicity in them. Does that answer your question? Okay. Yes, sir. That's good, because I probably don't know how to answer it. One of the assumptions that's made is that the interstellar medium is fairly homogeneous. Unless one of them is hiding behind a nebula, we're assuming they're passing through the same interstellar medium as all the other stars. I don't think redshift affects the brightness at all, so that's not going to be a factor. Any other questions?
I was wondering, in this, your electron diagram of changing levels, I assume if you're talking about an isotope, that it would have the same levels probably as the, the main.
I wouldn't think so because, actually I would think so because what determines how much energy it takes to knock it up the level is the amount of positive charge against which the negative electron has to fight. So you need that much energy to push it to a higher level. And since you're not going to have any more positive charge with an isotope.
Yeah, just more mass.
Yeah, right. And since it's, yeah,
Yeah, it might make a small shake.
yeah. It is, okay. If it's small, I doubt it's going to be noticeable at the resolution that I'm shooting, because like every pixel is 11 angstroms. I mean, if you get really good with this, you can get down to about 5 angstroms per pixel. All right, well, thank you all.
Well,
Appreciate it.
thank you. And we'd like to give a gift here.
Oh, thank you.
Okay. Hey, thank you, Don and Kevin. That was really good. I learned some things. It was nice. We all enjoyed it. Okay, this is mostly announcements about TAO, and TAO is Tamaki Island Observatory. For new folks, let's have a visitor. And so, for new folks, we have our stargazers at TAO, and sometimes there's other things, special events. The stargazers for the public are first and third Saturdays. So those are fun and pretty much unpredictable for a lot of reasons. One is the weather, more chaos than we want. But nevertheless, it's a lot of fun. We also have classes, special events. We sponsor International Friendship Stargazers, and we don't sponsor them, but we enjoy eclipses and occultations. So what you're going to find when you come up is a lot of astronomers setting up. This is an early shot. Thank you, Don. And this is from just a few days ago. We have some new things. This is very early. We're wandering around. New pads, and there's always something different going on. So that's new. And I sent a note out after it. So thanks went to a lot of people. Ted helped on the presentations in the classroom. Kevin got the big scope out, and that really helped. Art brought some music and his programmable telescope. Art, you can wave. I should introduce these things. Kevin, you can wave. Don, you can wave. Brought the drone and helped out. Noah was there. He showed us some star hopping. Bob discussed Orion activities, some benefits. Rob operated the Celestron, and George and Ricky were there helping us with surprising things. Anyway, it's a lot of fun. If you come up, you can use our scopes. You can bring your own scopes, and always surprises. So one of the things, if you, hopefully you enjoyed it, was the lunar eclipse. We had a lot of fun preparing. Some of us waited up late and enjoyed it, and some people took pictures. So all in all, it was a really nice event, I think. And I won't go over the surprises, but as I said, lots of good photos. The surprise I had, and I still don't understand it, is to me, there was a color change in the middle of the eclipse. The color was just a surprise. Maybe it was the fact the light was coming through the Earth's atmosphere, but the colors were a little bit off. So anybody else notice that? That's a prime example of where if we'd done the spectra and been able to look at the spectral change, we should have been able to see atmospheric lines, smog lines, maybe methane, probably not, maybe just certainly water. We'd see the water line coming out of the moon because that light's going through a lot of atmosphere, not only just one time coming back. So that would have been fun. Anyway, as I said, lots to see. Another thing is asteroid occultations. Those are always interesting. And to set up to get together in the classroom and ask ourselves, what did we forget? And leave it home. Why is it not going to work tonight? Are the clouds still there? And actually watch the changes as a star winks out because an asteroid moves across it. It's surprisingly interesting. We're having international fellowship stargazers also, ideally once a month. And they celebrate international friendship. So it's kind of fun. We have a international friendship belt in Oak Ridge Missile Park. Weighs about 4,000 pounds. It's bronze. And really, really a nice thing. To me, it's the most, maybe it's the only photogenic thing we can point people to, really photogenic thing. Oak Ridge is full of historic things, mostly behind fences. I've seen some of them and they're really neat, but way behind fences. And there in the center is Art. Art gets there early, that photo. So he usually brings his programmable scope, and he's got a nice smile, so he gets to appear in most of these photos here. But it's a nice thing we have to celebrate international friendship in Oak Ridge, I think. And this is another group. So in general, the groups are pretty friendly and congenial, even if we in this night arrive a little early. So timing is important. We choose it for the first quarter moon. So we've got about a week there, if weather permits, to get together. What else do we do? Well, we've been having astro lunches. We've been getting together, usually on a Monday at El Cantarito. And it starts out as an Orion board meeting. When it works that way, it's great. Sometimes it deteriorates into chit chat. We won't go into that, but they've been fun. Mission projects. The thing you see on the right is just is the output of a little radio. I built one for $20, so this big, can go in the shirt pocket. Turn it on, set it on a table, and it starts listening for other units and sending out beacon signals. Really inexpensive. And for those of us like myself, and like Kevin, and like Rob, that are just interested in radio astronomy, it's kind of a cute and interesting thing. So that little radio figured out a bunch of other radios around he could talk to and sent the picture to my cell phone. So that's Rob and I've been talking about it. Crazy little project, in addition to all the real astronomy projects. One more thing, this is over the past 4 weeks, I guess. We're putting up another display at the Oak Ridge Public Library. It looks like this without the captions at the top. Some of the usual suspects over on the right. And it'll be finished. We'll have the captions up, and thanks to Rob for the nice banner at the top. Hopefully that'll be up soon. Anybody worry about the stars in Orion?
It looked right to me, I don't know.
We have a debate about this.
Yes.
Anyway, that's fun. So another thing that's ongoing, and that's really what I wanted to show you, get a flavor of things. Anybody have any questions? Betelgeuse, as far as I know, is still kind of up there deciding what it wants to do in the future. I think it's kind of fun. You think about the spectra, what's it going to do? Well, yeah, it'll do what those stars do as they age, but everything nearby is going to get irradiated when Betelgeuse does something, and it's going to be sending out its characteristic spectra. So I think if we could look around it, that'd be kind of fun. There's also T Corboreal, and you can find the northern crown, Corona Borealis. That's going to have some excitement, and one star called the Blaze Star sometime soon is going to brighten up a little bit, factor of 1,000, like it does every 80 years. So, yeah. Larry?
Math is correct, that should be back in the morning sky again just before sunrise.
Oh, no, it's great. It's up right now.
T4 is up now.
Yes. It's a great thing for photography when the sun goes down. No, I've been watching it for a year. It's up now. It's great.
Is it near the horizon?
No, it's a good object after dark. I'm glad the question has come up. If I pull out my phone, and since it's kind of guiding us in Zoom, I don't want to do it. I've got astrospheric. I'm tracking T Corboreal. And so I can see what it's doing in the sky compared to where the moon is, along with other planets or whatever I put in. So if you download Astrospheric. I'll show you how. You can put that in. You can put your favorite sites in. I've got Tamki Allen in and a house, and Lily Bluff and Norris, things like that in here. And Orion now has a professional affiliated society status. So if you register with Orion, which is easy, you get the pro version on Astrospheric. So T-Core is easy to watch. I don't get any money for this. I should. Send money if you want. Okay. Anybody else? Great. Okay. Back to our president, Dr. Spong.
So I just thought I'd show a couple of astrophotos I'd done recently. This is the Heart Nebula on the left, which I didn't quite get the whole thing. It's a really big structure, but you can see most of it.
You want it done more done?
No, that's okay. And then the Jellyfish Nebula on the right, it was interesting in that you kind of blow this up and you can see these little shock fronts kind of it has a lot of structure to it if you enlarge it. And, from the initial supernova, when it blew up, it created all these little shock fronts in the exploding gas. You can kind of pick those out, even though it's been around for quite some time.
What's on the lower left? Is that a separate nebula or is that part of this?
I think you're talking about this?
Yeah.
John, is that the heart and soul?
Well, this is the heart. The soul is nearby. I don't quite remember how far away it is, but it's yeah, no soul at this point, but I'll work on that later. And then just this weekend, some of you saw I was working on this object, NGC 4449. It's called an irregular Magellanic type galaxy. It's in the constellation Canis Venatici, about 13 million light years away. So it's not a real big thing, but it has kind of interesting structure to it. And then to get something that was easier to image, I switched over. This one got to the point that it was straight overhead and my mount won't track, so I had to wait till it could do a meridian flip to get it from the other side. So while I was waiting for that, I worked on Bode's galaxy a little bit, M81. And so that's a grand design spiral galaxy about 12 million light years away in Ursa Major. And of course, it's in a good position to be seen right now. And both of them could use more exposure time, but that's just what I've gotten so far. Yeah.
How much exposure time do you have on both galaxies?
I think it was like 30 or 40 minutes, 60 seconds each. And this is using my 8-inch Celestron with the 0.7 focal length reducer to get a little bigger view than the standard. The other thing I wanted to mention, since several people here have the C-Star, is they've just recently, in the last few software upgrades, they've started giving you the option of putting this on a wedge configuration. People were kind of doing this informally on their own, but if you don't have the support from the software, it doesn't really help you too much. So you can buy this. I have a thing from Skywatcher that I bought here to put it to allow it to tilt back like this, and so that way it acts like an equatorial mount, because you can aim it at Polaris and it only has to move in one direction, of course, to track the stars.
Does that give you a smoother astrophotography?
Yeah. So you go through the menus and you just go to the mount mode and select equatorial instead of alt azimuth. and it'll give you a little diagram showing how you need to change the tilt. This one, I think I had it turned around the wrong way or something, so it was way off here. But and then you take a picture of the stars. It takes pictures right overhead, and it tells you what the azimuth, how far you are off on the azimuth. And so you can tweak it with this little attachment and get it kind of pretty well polar aligned. Now, I had one night I got it pretty well aligned. The second time this weekend I was having trouble getting it to get a good polar alignment, but it still does pretty good. And they now have a menu that you can go up to a 60-second exposure, whereas previously they only had 10 and 20-second exposures. Now I don't think I've gotten the 60-second exposure to work. It complained it was getting star trails even with this equatorial orientation, but I think with work I can get it so it'll do 60 seconds. And of course the advantage also of this is you don't get this what they call field rotation that you get with all azimuth mounts. So you can take longer integrated exposures.
I have a practical question.
Mhm.
Do you have any trouble with the thing getting too deep?
Yeah, that is a problem. I mean, I think what they recommend is you have one leg of the tripod pointing north. There's a certain orientation that makes it less tippy, and I need to be more careful about that too. But yeah, you could hang a weight from it or something to stabilize it, certainly. So anyway, these are a few images I took in this equatorial mode, and they came out pretty well. M51, M3, the star cluster, and then Bode's and the cigar galaxies. So I could fit both of those on one image here, whereas on the big telescope I could only get Bode's galaxy by itself. And I took this while I was visiting my daughter in San Francisco. It's easy with this C-Star just to put it in your suitcase and take it places. So it got through the trip to San Francisco and back and still was doing fine. So
Wait a minute. You took that to San Francisco?
yeah,
What was the portals of the sky?
it's not too bad there. I took it from their backyard and it's fairly dark. Even there in the city, it's. I mean, it was looking fairly straight up at that time, I think. But
In the dry season.
okay, so that's all I had to show. And, close it.